Hello everyone. Today we will discuss about Newton's laws of motion. The Newton's laws of motion are very important in order to understand classical mechanics. And we all know that mechanics is the backbone of many branches of engineering such as mechanical engineering, civil engineering, etc. So it is very important to understand Newton's laws of motion. Now, as I have mentioned in my previous lectures, I will explain the concepts using vectors, calculus, because I believe that if you approach any concept or any problem in physics using vectors or calculus, then you can solve, first of all, you understand the concept very deeply, and if you were to solve any difficult problem, you can solve it very easily. So let's start understanding the concept. So Newton's first law of motion states that the acceleration vector of a body is zero if the total vector sum of all the forces acting on the body is zero. So if the total vector sum of all the forces acting on the body is zero, then the body either remains at the state of rest or it moves at a uniform velocity. The body does not accelerate. Newton's second law of motion states that if the vector sum of all the forces acting on the body is not equal to zero, then the body accelerates. And the relationship between the acceleration of the body and the vector sum of all the forces acting on the body is given by this equation. So this equation is mass times acceleration vector of the body is equal to summation of all the forces, vector sum of all the forces acting on the body. Newton's third law of motion states that if there are two bodies A and B, and if body A exerts a force F on body B, then body B will also exert a force F on body A. So let's understand this with the help of a practical example. So let's say there is a needle and we press our finger against the needle, then we feel the pinch of the needle. So why do we feel so? So we apply a force F on the needle, and in turn the tip of the needle applies a force F back on our finger. Now since the tip of the needle is having a very small area, so that entire force is concentrated over a very small area, so we experience a very high pressure, and that's why we feel the pinch. So this is because of Newton's third law of motion. Now all the three laws of motion are applicable from an inertial frame of reference. So first of all, what is the frame of reference? A frame of reference, as I explained in my previous lecture on relative velocity, a frame of reference is any place from which we make an observation. So let's say right now I'm standing on a ground and observing something in the sky, then the ground becomes my frame of reference. I might be sitting inside a moving car and observing something outside, then the moving car becomes my frame of reference. So frame of reference is any place from where we make an observation. By definition and by convention, we will consider Earth to be an inertial frame of reference where all the three laws of Newton's law of motion will be applicable. So this is by convention. So don't ask why do we use the term inertial frame of reference. It's just by convention we consider Earth to be an inertial frame of reference where all the three laws of motion are applicable. Now, not only Earth, any frame of reference which moves or which does not accelerate with respect to an inertial frame of reference is also an inertial frame of reference. So, for example, let's say, as I mentioned, Earth is an inertial frame of reference, and let's say there is a car, parked idle on the ground. Then for a person sitting inside that car, that car will also be an inertial frame of reference because that car is at rest. Now let's say that same car starts to move at a uniform velocity, then again for the same person, that car will be an inertial frame of reference because that car is still not accelerating. However, if the car starts to accelerate, then that car no longer is an inertial frame of reference, and the car becomes a non-inertial frame of reference. And Newton's laws cannot be directly applied in a non-inertial frame of reference. Now let's understand how to apply Newton's laws in a non-inertial frame of reference. So let's say I'm, as I mentioned, standing on the ground here. Let me call this as G, and there is a car which I discussed earlier. Let's say this is the car, and this car is accelerating in this direction. And let's say there is a point P, which is having a mass m, right? And this point we are observing from the ground as well as the car. So let me first fix the coordinate system with respect to the ground. Well, in physics, any problem you like or any concept you approach, always start the coordinate system. It will make the life much easier. So let me have x or y as the coordinate system with respect to ground, and uh, x dash, o dash, and y dash be the coordinate system with respect to the car. Now the position vector of this point P with respect to the car will be given by this vector, which is O dash P vector. Let me call this vector as R vector P with respect to car. The position vector of point P with respect to ground will be given by OP vector. Let me call this R vector P with respect to ground, and the position vector of the car with respect to the ground will be given by O dash vector. Let me call this R vector car with respect to the ground. As I explained in my last lecture on relative velocity, same concept is applied here. This O dash and P form a vector triangle. So by the law of vector addition, R vector P with respect to G is the sum of R vector P with respect to C and R vector C with respect to G. If I double differentiate this equation, then I will get what? I will get acceleration vector of P with respect to G is equal to acceleration vector of P with respect to C plus acceleration vector of C with respect to G. And so this equation I can rewrite as acceleration vector of P with respect to the car is equal to the acceleration vector of point P with respect to ground minus acceleration vector of the car with respect to the ground. Well, now if I multiply this both sides of this equation by the mass of the particle, then I get mass times acceleration vector of the mass m with respect to the car is equal to mass times acceleration of the point P with respect to ground minus mass times acceleration of car with respect to ground. Now this term m a vector P with respect to C is what? This term is basically mass times the acceleration vector of the point P with respect to the car, which is a non-inertial frame, this term mass times acceleration vector of P with respect to ground. So this is the acceleration with respect to an inertial frame. So since this is mass times acceleration with respect to an inertial frame, I can apply Newton's second law. And replace this term by summation of all the vector sum of all the forces. So let me rewrite this equation as mass times acceleration vector of point P with respect to car, which is a non-inertial frame, is equal to vector sum of all the forces acting on the point or on the mass m minus mass times acceleration vector of car with respect to ground, which is basically the acceleration of the non-inertial frame with respect to the inertial frame. So now if you compare this equation with this equation, basically we observe that there is an additional term in a non-inertial frame. There is an additional term which we add, which is minus m times the acceleration vector of the non-inertial frame with respect to the inertial frame. Now this term has the unit of force. So it is not an actual force, it has the unit of force. So we will call this term as a fictitious force or a pseudo force. So this is the pseudo force, right? So this equation says that if we observe an object from a non-inertial frame, then the mass times the acceleration of the object in a non-inertial frame is equal to the vector sum of all the forces acting on the body plus a pseudo force which we have to apply on it. Then Newton's laws can be applied from a non-inertial frame of reference, and the magnitude of the pseudo force will be given by the mass of the object under observation times the acceleration of the non-inertial frame, and the direction of the pseudo force will be opposite to the direction of the acceleration of the non-inertial frame. Now in the next lecture we will understand these concepts with the help of an example.